Now we're going to consider the effects of molecular shape on how one covalent compound interacts with other covalent compounds that surround it. Remember, unlike an ionic compound, covalent compounds are constantly surrounded by other molecules and they come in contact with them, but they're not stuck to them directly. This is dependent on how electronegativity would be found within that molecule. So if you can remember, we talked about electronegativity. Fluorine is the most electronegative. Things increase this way, electronegativity increases this way, and up the periodic table. So in general, the closer that something is in range of fluorine, the more electronegative it is. When you have a bond that is a covalent bond, okay, so let's say that they're both equally sharing, that means that one atom is not more electronegative than the other. But if one molecule, or one atom of the molecule is greedy, he wants to have more electrons towards his side of the sandbox, if you will, he pulls the other one in his direction, okay? Here's what happens. Fluorine you can consider to be the most greedy of the atoms. He is so close to having that perfect octet. He will do anything to get it. He'll share a bond, but really he wants to take over the vast majority of it. And so a lot of that electron density gets pulled with fluorine, and that's what we have to create polarity in a molecule. So if you have a polar bond, you might have something like HF, but fluorine's going to pull electrons towards himself. And we actually draw something like this. We say that the electrons go towards that way, and it leaves behind a little bit of a positive charge on that hydrogen. Now these are not actual charges of plus and minus. Instead, they're partial charges of plus and minus. So another way to show that, this guy comes in as partially positive, and fluorine comes in as partially negative, because remember, he's pulling something towards him that has a negative charge. On the other hand, if you have something that's nonpolar, such as HH, they're going to pull the same amount. They're equal. So this is a nonpolar bond. If you think of things that are gases, H2, O2, CO2, N2, these tend to be nonpolar bonds, okay? And I'll talk about why in a little bit. The definition of nonpolar bonds is kind of what CH is. So these CH types of molecules are going to be nonpolar. There's many variations within a compound, and that's possible, and it's totally fine. So here we have a carbon with 3 hydrogens surrounding him, but a chlorine's over here. Well, chlorine, if you recall, is directly underneath fluorine. Chlorine's electronegative. CH, as we said, those are nonpolar, so we don't have to worry about those. But this bond is going to kind of pull electrons towards this side of the molecule. So electron density will move towards the chlorine and away from the carbon itself. And that's what this little arrow means. Another way to denote that is these partial negative and partial positive types of sort of signatures. So this sort of looks like a funky little S that has a plus charge to it, and this is a funky little S that has a negative charge to it. So partially negative, partially positive. Okay, well, when you have things that are partially positive and partially negative, that's going to make a difference as to how things look in bulk. Okay. Now, before we get into that, I want you to think about the fact that your polarity can be influenced by the shape of your molecule. If you have something like water, remember from last time, that is bent. Oxygen is more electronegative than hydrogen is. Oxygen's here, hydrogen's way over on the other side. Oxygen is going to pull electrons towards the oxygen itself. So in other words, there's a bond that goes this way, and electrons are being pulled this direction, electrons are being pulled this direction, and if you want to consider it that way, what's happening when two things pull in these directions? It's actually a net force of going up. So another way to write this would be an overall pull upwards with a positive charge down that way. So this is going to give a partial negative charge to this oxygen and a partial positive charge to each of these. Here's why I mention the molecular geometry as being so important. Because now let's consider CO2 as the example. So that's what this guy looks like. He's linear. If you've got an oxygen that's pulling electrons this way and another oxygen that's pulling electrons this way at the same amount of force in both directions, they cancel each other out. There's not an actual direction that that molecule has its electrons built up. So these are basically going to cancel each other out and not give you anything. That's why water being bent is so important. Because these polarities give rise to different types of intermolecular forces. Intermolecular forces is how one of these molecules interact with other molecules that surround it. Okay? So, let's talk about those intermolecular forces. The strongest thing that we can somewhat consider intermolecular, but really it's part of the ionic bond, is that you have something that's positive, negative, that would be an ionic compound. Those stick together because they're like magnets, right? So positive and negative stick together, no problem. If, on the other hand, you have something with a dipole, di means two, that means positive, negative, right? But these aren't actual ionic bonds. They're partial charges, not actual charges. But if we look at how this structure of this particular molecule has a dipole, positive end and a negative end, that lets these guys kind of stick together like little magnets, not like the real magnet, like partial magnets. That means that they're going to stick together more. That means that these molecules, the way they behave when they come together like a cup of something, is going to behave differently. Now, there's the special type of dipole bonding that's very important. Why? Because water's involved. And other things too. But hydrogen bonding is this special thing that happens when you have an oxygen, nitrogen, or fluorine attached to hydrogen. Oh, I see all these little dots that I have right here. That is sort of like special magnets that are stronger than your normal dipole-dipole bond. They are not the same thing as an ionic bond, but they're kind of somewhere in between. And it is quite a bit stronger. Evidence. Water is H2O. It's really small, but because of hydrogen bonding, it has a boiling point of about 100. On the other hand, H2S, that's bigger and should, you would think that that means that if it's bigger, it has more mass, that it would have a boiling point that's a little bit different. This guy becomes a liquid. I'm sorry, I said boiling point. This one has a liquid state at up to 100 degrees. Yeah, boiling point, 100 degrees, good. This one's like negative 32. It's way lower. So this is a gas at room temperature. This one's a liquid. He's smaller. Okay. again, important for you to exist. The dots represent how these two molecules interact. It is not an actual bond, but it's kind of like they go through holding hands from one to the next and go, hey, I'm glad you're here, okay? They're constantly sort of interacting with each other, and it's a pretty strong interaction. They're like social little bees, okay? On the other extreme are these things called dispersion forces. Now, we try to talk about how the electrons can go to one side of the molecule and cause a temporary partial negative or partial positive charge, and that's what keeps things together. And that's true, but for your purposes of understanding what that means, I want you to just consider it, hey, there's nothing really there. Okay, so there's not really something to stick these things together. I think of dispersion forces as being similar to what puts those little balls together in the place where you jump, kids jump into the balls and they go exploding everywhere. They're not really stuck together by anything other than the fact that they're in that little play area, okay? So how well these molecules stick together makes a difference in what their boiling point is or what their melting point is. And when you have things that don't stick together very well at all, like dispersion forces, that means it's going to be a low boiling point or melting point. Ionic compounds have melting points that are hugely high. But you should find things like hydrogen bonds have a higher melting point than others do, or they stick together relatively well. And dipole-dipole bonds are sort of here in the middle as well. Okay? Thank you very much.